Review sheet. There we go. Okay, you guys ready? All right, so it says up at the top, consider a collision between a small car and a heavy truck. In such a collision, how does the size of the force exerted on the car by the truck compare with the size of the force exerted on the truck by the car? What do you guys think? Should it be different or should it be the same? So this, when we're talking about the force that two objects exert on each other, this is called a Newton's third law pair. Bless you. Right? Where Newton's third law says that for every action, there's an equal and opposite reaction. And those two actions are going to happen on two different objects. So these two forces are going to be equal. The car on the truck is going to be equal to the size of the force on the truck by the car. You guys have any questions about that one? It seems kind of familiar, at least. Hopefully, yeah. Okay. For the second one, it says draw a velocity versus time graph for a ball that's thrown vertically into the air during its up and down motion. So you guys have thrown balls into the air, right? Not our bowling balls from the beginning of the month, but like a baseball or something. And it goes up and then it reaches a velocity of 0 and then falls back down, right? Where's our ball moving the fastest? Yeah, it's going to be the fastest right when you let go of it, when you throw it up, right? And then slows down as you move up. And then at the top of the throw, it's going to have a velocity of 0 and then accelerate downward. So the biggest magnitude for the velocity is going to be at the top and the bottom of the throw, the beginning and the end. And so when we draw our velocity versus time graph, it's going to be where the ball is at its peak that it hits 0. Right? So this is where we're at peak. And the beginning and end of the throw is where it's going to be high. So here we have a large magnitude for velocity. And we're going to have the same magnitude for velocity on the other side. So I just put some dots in there. And then I would expect that I'm going to have a line that looks like that. So if I throw something up in the air, I'm going to start with a high positive velocity because the ball's moving in the positive direction. It's going up. Then when it reaches the peak, it's going to have a velocity of 0. It's going to have a split second where it just hangs in the air and has no velocity. And then it's going to have a negative velocity as it falls back to the earth. And because we know that things accelerate as they go towards the earth, the velocity is going to get greater in magnitude, but stay negative because negative tells us about direction. So here we've got draw a force diagram for the ball when it reaches its highest point. What forces is our ball experiencing when it hits that highest point?
Excuse me, can we get Kim Washball to the office for a moment, please?
Yes.
Thank you.
And so when it gets that highest point, what force is our ball experiencing? It's on Earth, guys. Uh-oh. Gravity, yeah. So there's our ball, and it's going to be experiencing a force due to gravity because gravity is always going to be pulling objects downward with a negative acceleration. So at the highest point is the velocity 0. Yes. One way we know is because it's changing direction, right? So when it's changing vertical direction, it has to have a point where if you go from moving in a positive direction to a negative direction, you have to pass through 0 to get there, right? See, it goes from to negative must. We could use this graph to explain that. that we know that we start with a positive velocity, we end with a negative velocity, we have to go through 0 in the center. We could also talk about the position versus time graph for this. So if we've got position and time, that our ball is going to have this kind of motion. And so the slope at the peak is 0. And because that slope tells us about velocity, then we know that the velocity has to be 0. It says that the highest point is the acceleration 0. Explain. The answer for that would be no. And the reason is because on Earth, or on any planet really, but on Earth, there's always going to be acceleration due to gravity. Always. So that's always going to be pulling objects downward. The other way that you could know is because if you made an acceleration versus time graph of our velocity versus time graph, you can see that this is a constant negative slope. So if this was 0, we would have a constant slope down here. And so we would be able to tell from looking at our velocity versus time graph that our acceleration should always be negative, which means it always exists, right? It's always there. At the highest point is the net force 0, or all the forces balanced. What would balance tell us? What would that tell us about acceleration? If our net force is 0 newtons, that tells us that our object has balanced forces. Balanced forces also mean because net force is equal to mass times acceleration, because that's true. If we've got balanced forces, that tells us our acceleration has to be 0. Because we can't have an object that has 0 mass. That's not a thing. Breaks the rules. And so at the highest point, can these be balanced? Well, we know that there's an acceleration in place. And if there's an acceleration happening, then they can't be balanced. So if there is Does that make sense? How do you guys feel about that? Feel okay about it? You guys are quiet today. It's even like dress down day for seniors. You guys are still quiet. All right. The figure below is a snapshot looking down at a bowling ball, moving at a constant velocity from left to right on a smooth, level floor. In the position shown, the ball is given a short, sharp hit in a direction perpendicular to the ball's initial motion. You guys see the arrows down here? What this question is asking us to do, it says on the diagram, draw a path that the ball might follow after the hit. Explain your reasoning for the path you drew. And so what we need to do here is just connect these vectors and figure out where our ball is going to go. So to do that, I'm going to kind of reimagine this a little bit. We already know that our bowling ball, is traveling with velocity to the right. But this arrow that it's hit by also indicates that now it's going to also be traveling upwards a little bit. So we're going to do that thing like we did when we were trying to figure out vectors. These are two components that we have to add together to make a final vector. So I'm going to repeat it on this side. I'm going to repeat that initial velocity line crest here. And so I can figure out that my final vector should be, see, this pen is busted, it always does it. My final vector should be this direction. Have you guys ever noticed this when you're playing pool, maybe? If you're playing pool on a table and you have a ball that's moving and then you roll another ball towards it, you get a new direction. It's kind of the average between the two. So now our object is moving up and to the right. I'm going to do this. Let's see. I'm going to treat orange and blue as two vectors. Oops, two vectors. And says, next question. Immediately after the hit, will the speed of the ball be equal to, greater than, or smaller than the ball's velocity before the hit? And explain your reasoning. Well, if we have an object that's traveling the direction and magnitude of the blue arrow, and then we hit it with this orange arrow, what we're going to end up with is not just the direction, but also the magnitude of the pink arrow. So it's going to add a little bit of velocity, but it's not going to be as much as doubling it. And so you would have to do, some trig to figure that out. So it says, will it be equal to, greater than, or smaller than the velocity before? And I'm going to say it will be greater than. So I wrote the new vector was going to be the hypotenuse of this triangle, and so I know that it's going to be larger than the initial magnitude was. Do you guys have any questions about this one? And it's a little bit conceptual. How will the velocity of the ball behave as time goes by after the blow? That is, will either the magnitude or the direction of the velocity change? If so, how? So in order to think about that, what we need to do is understand if that ball is experiencing any forces other than that initial force from the hit. And so it says it's on a smooth, level floor. So if you've ever gone and actually bowled, have you guys ever noticed the ball will just keep rolling, no matter how hard you throw it? And so I know most people try to throw it pretty hard, right? My son loves bowling. He's 8 now, but when he was like 5, we took him bowling, and the ball took 4 minutes to get to the end. I timed it. 4 minutes in bowling is an eternity. It took forever, but the ball got there. And the reason it got there is because people put oils and things on that surface so that there's no friction. Just like we're going to have low friction this weekend. And so here, the ball, as time goes by, as long as the surface is smooth and level, there's not going to be any forces opposing that motion. And so unless there are forces that oppose that motion, it's not going to slow down. And so if it's perfectly smooth, it won't slow down. We know that probably eventually, if it was an infinite bowling ball lane, it probably would slow down, right, at the end, because there's going to be something that causes the problem. But generally, if the floor is perfectly smooth, it's not going to slow down because there's no forces opposing the motion of the ball. It's really better here to just say the motion of the ball instead of the forces, because after the ball is rolling, there's no force being applied to the ball except for gravity and normal force, 2 vertical forces, and no horizontal forces are being applied. Do you guys have any questions about the bowling ball? Okay. Ooh, the shopping cart problem. Do you guys like doing this one? This is a little bit different way to think about it because there's lots of, you have to kind of think about what's happening with each figure in this problem. Okay. So you push a grocery cart along a level floor in the presence of friction effects between the cart and the floor. Draw force diagrams for you, the cart, and the floor, earth. Fully label all vectors. All right. So let's see, where should we start? The person, the floor, or the floor/earth, or the cart? What do you guys think? Anybody? I kind of like to start with the cart. I don't know. It's kind of an easier one to think about because that's the thing that I'm interacting with. And so I know that the cart is going to have gravity, normal force, N, right? Because it's always there. I also know that it's experiencing a push from me. So I'm going to push it forward. It's going to be experiencing some friction, right? Friction in the wheels, though, that's a weird one because it's going to make it go forward, right? You guys remember that part? Yeah. Is it accelerating, though? Actually, it doesn't say. There might be some friction in the wheels pushing backwards, too, because the bearings will have some friction, but we'll just move on from there. I know that I am experiencing gravity. I'm experiencing normal force. I'm pushing the cart, but the cart is also pushing back on me, right? And you could call that a push. You could call it a normal force. Doesn't really matter. Anything making me go forward? Maybe a little bit of friction when I'm walking. What about the earth/floor? This is going to be kind of backwards. The earth is experiencing a gravitational force from me. It's experiencing a gravitational force from the cart. That's pretty weird, right? It's experiencing normal forces from me and from the cart. Is the earth experiencing any sideways forces? I don't think so. We can also look for Newton's third law of pairs in here. So one of these is going to be the gravity on me. It's going to be the same as gravity, equal and opposite to the gravity that the earth is experiencing from me. Normal force on me from the earth is going to be the same as normal force on the earth from me. We're going to have these pairs too. Those are connected to each other. And then the push on me from the cart is going to be equal to the force on the cart from me. Using different colors here too. I'm a little bit bothered by the fact that I don't have one drawn pushing back this way. I think maybe there's some kind of friction there or something that's keeping it from accelerating farther. It might even be pulls backward for me. Do you guys ever control a cart that way? You pull it back so it doesn't take off. Maybe that's just me because I'm a parent. My kids are always hanging on the cart. My kids are always applying forces to the cart to make the cart go in a direction I don't want it to go, so I have to pull it back. So there's probably something else happening here. So there has to be if this thing is not accelerating. The other possibility is that if the forces are balanced, that these forces are really small, right? If I make those smaller, then it's possible that friction backward may be enough to keep it from moving at a constant rate. Because if we have something that's experiencing friction, if I put something down on the table and then I push it, there's going to be some friction there, and I only need to push it hard enough to overcome friction. I think that's probably what most of us are doing with our shopping carts. We push it just enough to make it go. And so we are sort of sensing what that amount of force needs to be, because I know that I don't accelerate the entire time I'm pushing a grocery cart. I don't know about you guys. I only accelerate a little bit. Okay, you guys have any questions about that? We're doing okay so far? You guys are really quiet, so I'm a little worried about you. Okay, it says when you are making the cart speed up when we're accelerating, how does the size of the force you apply on the cart compare to the size of the force the cart exerts on you? Well, what did we say before? Is that the force that I apply on that object is going to be the same as the force that object is applying on me. So those two forces are going to be equal. If we want the cart to speed up, what's going to have to change is not the pair of the push on me by the cart and the push on the cart by me. It's going to have to do with this friction forward and friction that's pulling it back. It's going to be the sum of the other horizontal forces that are making the difference there to make it speed up. While you're making the cart speed up, it's going to accelerate. How does the size of the frictional force on the cart by the floor compare to the frictional force on you by the floor? What do you guys think about that one? Force on the cart by the floor. So we've got friction. Compare to the frictional force on you by the floor. Do they have to be the same? Do they have to be different? Do they have to be zero? You guys think? I don't think those things have to be equal, right? Those aren't a Newton's third law pair, because we're not talking about the interaction of two objects with each other. We're talking about the interaction of two objects with something else, right? So these are not a Newton's third law pair. And these are probably going to be dependent on the mass of you in the cart, right? Some days you might be heavier than the cart, and some days you might be lighter. But just like we did that experiment with the gym shoes, right? We could change the friction by changing the mass of the object. And so that would probably make a difference there. And then down at the bottom, it says, identify all the Newton's third law pairs in your force diagrams. I kind of did that with colors and slashes. So the ones that were orange that were associated with me, I matched up with the forces on the floor / earth. The blue ones are matched up with the cart, and then I have a single black one that's connecting the cart and me together. The other ways you could do this is you could put little labels on them. You could call them A, B, C, D. You could just use number of slashes. I kind of knew that there was going to be a bunch of pairs. So there's 1, 2, 3, 4, 5 pairs. And so I didn't want to end up with 5 slashes on a line. So that's why I use colors. And that's all okay. Do you guys have any questions about number 4? No? Okay. Back page. There's a kid with a wagon. They're trying to go up a hill at a constant speed. The wagon exerts 60 newtons of force on the kid. First step, draw a quantitative force diagram for the wagon. So I know that my wagon is going to be experiencing gravity. My wagon is going to experience normal force. My wagon is exerting a force on the child, right? But I don't need to know about that. I need to know the force of the child on the wagon, which is going to be this one. Force child. Sounds kind of aggressive. What on earth? Okay. All right, so now we need to figure out what's going on with this thing. So we've got gravity. Can we figure out a value for gravity? We can, because it says that our wagon weighs 12 kilograms. So this is going to be 12 kilograms times negative 10 meters per second squared, which means that force due to gravity is minus 120 newtons. We've got backwards force of the child. Sounds like Mandalorian stuff. 60 newtons that way. We've got a normal force this way. Okay, this is quantitative, so it wants us to figure these out. So if it's going to be quantitative, we need to figure out this normal force. The way that we're going to do that is we're going to put this on an axis, right? And we're going to use the lines that are parallel and perpendicular to the surface to figure that out. Come on, camera. There we go. So here is one axis along the surface. The other one's perpendicular surface, so it goes right through normal force. I'm going to make my rectangle. Careful with your rectangles, guys. This is something I saw a couple of times on that quiz. So you want to make sure you draw your rectangle so that the force that is not on your axis is the diagonal line of your rectangle. And then we can draw our components for gravity. So here's force of gravity in the vertical direction and force of gravity in the horizontal direction. And if I want to solve for normal force, I need to solve for FGY. I know that down here I have an angle of 30 degrees, which means my angle up there is going to be 60 degrees. So if I want to solve for FGY, I could use 60 or I could use 30. No, I'm going to use 30. FGY is the adjacent leg, so I'm going to use cosine. So the cosine of 30 degrees is equal to the length of the adjacent leg, FGY, divided by the length of the hypotenuse, which is 120 newtons. So be careful with this too. I saw a few people on the quiz had put them upside down. They had either not identified correctly which one was the hypotenuse, or they inverted the trig identity. So just be careful about that. So if I want to solve for FGY, I'm going to do minus 120 newtons times cosine of 30. So I got minus 103.9 newtons. Well, if FGY is 103.9, then I know that FN has to be positive 103.9 newtons. What did you guys do? Did you get that? 103.9. All right, explain how we use Newton's first law to make the force diagram quantitative. You guys remember Newton's first law? No. Do you guys really not know Newton's first law? I'm worried this is going to be a problem on Monday. Go ahead, Nathan. Okay, that's good. Is there is there a way that we use that to make this force diagram quantitative? I know Newton's first law is like the least used of the laws, right? We kind of intuitively believe that, but well, if we're gonna say that, let's see, um, an object in motion will stay in motion, an object at rest will stay at rest, unless acted on by an outside force. And so we are gonna kind of make some assumptions if we're told things like, um, if we're told that it's moving at this speed, at the speed of 0.6 meters per second, we're going to assume that it keeps moving at that speed, right? If there's not a force being applied to it. And so in the absence of a different force, we're going to assume that that is a situation that's balanced. We're going to assume that the velocity doesn't change. And that leads us to believe that this is a balanced situation, which is what makes us say things like, well, these two forces, the component of gravity that's down into the hill and normal force up from the hill should be balanced, because it shouldn't change unless another force is applied, and we have no evidence that there's another force being applied. And so that's kind of how you would work through that. So let's see, let's just jot down object in motion, stays in motion. Yeah, so I'm going to write on here, forces that are balanced stay balanced without other forces. Okay, and this is explain how you applied Newton's third law to make the force diagram quantitative. So Newton's third law is for every action, there's an equal and opposite reaction, right? And so I'm going to write, change colors. So how did we use that idea? It was kind of subtle. Up here, we were told that the wagon exerts 60 newtons of force on the child. But when we were drawing our force diagram, we were drawing a force diagram for the wagon. And so we said, well, if the wagon exerts 60 newtons of force on the child, then the child exerts 60 newtons of force on the wagon. I just spelled exerts wrong. Exerts. And so that's how we use Newton's third law, is that we're like, well, if we know that there is a force from the wagon on the child of 60 newtons, that the force on the wagon from the child has to be also 60 newtons. You guys have any questions about number 5? How you guys feel about Monday? We got this? Okay. The winning team in a tug of war contest is the team that puts more force on the rope. Is that true? Have you guys ever been in a tug of war? What do you look for in your tug of war teammates? It's related to that shoe lab, by the way. What do you look for? Michael has an idea. That shoe lab we did the other day. You need good friction on your shoes, right? What else do you need? Every team does this. Come on, you guys tug of war. You guys ever like try to get the like biggest guy on the team, and then you like tie the rope to him? Have you guys ever done this? When I was in high school, we would have we would go on a senior trip every year that was a couple of days, and we would always have this like obstacle race course thing. It's on YouTube now. For the year that I did it, some kid was sneaking in a video camera the entire year. But it was a relay that took like an hour, and there were 3 teams in the relay, and then if you were in the top 2 teams, there was a tug of war to figure out who won at the end. And so, like you always take the most the most massive kid and put them on the end of the rope, and then everybody else lines up. Our strategy was to line up people in terms of like who had the grippiest shoes, and the grippiest shoes went to the back. and you've always got people who like forget to bring their tennis shoes on senior trip or something, and they're wearing like really slippery like flip-flops. Flip-flops are not good shoes to take to a tug of war tournament, right? Because they'll fall off your feet. You can't stay in them. So winning team in a tug of war is the team that puts more force on the rope. Why is there a problem with that? If you've got a bunch of people and they're pulling on a rope, right? What's Newton's third law say? Newton's third law says for every action, there's an equal and opposite reaction. So if these people are pulling on the rope and these people are pulling on the rope, they're pulling on the rope with the same amount of force. This pull is going to be equal to this pull. The place where you're going to make a difference with your tug of war is who's pulling back, right? We don't really care so much about pulling on the rope. We are just trying to put as much force as we can so that we're pulling backwards from each other, right? When we did it in high school, by the way, it was always over a creek. There was this creek at the camp we would always go to. And so whoever lost ended up in the creek in the middle. I did not end up in the creek. So, yay. Okay. Do you guys have any questions about any of those? How do you feel about Monday? Feel okay? All right. If you guys have questions on stuff, I'm going to be posting a bunch of like the videos over all the stuff that we've done. What I'm expecting you to be able to do is draw force diagrams on an angle or not, be able to figure out quantitatively what's going on with your force diagram, so be able to calculate the forces, and then be familiar enough with Newton's third laws that you could answer a question in terms of applying one of those laws to one of those problems. That's where we're looking. I'll post those videos for you guys over the weekend. If you have any questions over the weekend and you want to get a hold of me, using Remind is the best way to do that because I almost always have my phone with me, but not necessarily my email. I believe there's still instructions for signing up for Remind on Google Classroom. So if you haven't done that at this point, you still can. Oh, you guys want to check the weather forecast? Why not? It's fun, right? I should just make this a button at this point. Look at that, guys. Oh, it got bigger. It got worse. Look, we're almost going to certainly have snow by 7 p.m. tomorrow night. And this says occasional. So like our likelihood of having this, you guys see the percentages up here? It's above 95%. And it's saying 4.2 inches of snow. That's kind of exciting. Have you guys ever had that much snow in your lifetimes here? It used to be common. Like I remember snow that was knee deep. Uh-oh, and look at this. That's going to be nasty. So, make sure you take your stuff home. I don't know. Maybe we'll have a snow day on Monday. Do you guys want to have a snow day on Monday? I know it's not really something any of us can vote for, and no one cares about my opinion, but that looks crazy. So if you have a long-term assignment, maybe make sure you take that stuff home too, because you might get a free day. Oh, that's bad. That means I have to bury the crab before it starts snowing. Dang it. My daughter will want to bury it. I have to call the pet place and be like, I've had this crab for like 35 days. Like, can I have another one? Some pet places do that. Anyhow, I hope that you guys have a nice weekend and you enjoy the snowy weather and it doesn't cause any issues at your house. Our pipes like to freeze on our second floor. Stupid pipes.